Hello everyone, welcome to RN tutorials on mechanics of solids. And in this video I'm going to discuss about elastic moduli, means different types of elastic modulus, and what is lateral strain and what is Poisson's ratio, and the derivation part related to relation between different types of elastic modulus, that is elastic moduli. Okay, so first I would like to mention what are the different types of elastic modulus we have. So there are mainly three types of elastic modulus. The first one is Young's modulus of elasticity, and second one is modulus of rigidity, and the third one is bulk modulus of elasticity. And again, these three types are classified based upon the type of the stress that is going to take place whenever we apply the load over the body. So now we try to have a look over the definition for each and every elastic modulus. So first one is Young's modulus of elasticity. A simple definition we can give to the Young's modulus of elasticity as it is defined as a ratio of tensile stress to tensile strain or compressive stress to compressive strain. This is the definition similar to the modulus of elasticity or elastic modulus, which is the ratio between the stress and strain. And based upon here, the type of stress we are considering, we are defining the Young's modulus of elasticity. So, what are the types of stresses we are considering here for Young's modulus of elasticity? That they are tensile stress and compressive stress. So, accordingly, tensile strain and compressive strain happens within the body according to the type of load we apply, that is tensile force or compressive force. So, related to this tensile and compressive, the ratio between the stress and the strain can be called as here Young's modulus of elasticity. Okay, the formula we can write simply. So before that, I have given the symbol which is used to represent the Young's modulus of elasticity. So it is denoted by capital E. Okay, so this capital E is equal to formula what we can write as sigma T divided by ET. Sigma T means which is the tensile stress and ET means tensile strain. Okay, sigma is the symbol used for stress and E is the symbol used for strain. So here the suffix T is given because it is related to tensile stress. Okay, this is one equation, and in the form of compressive stress and compressive strain also we can express. So or it can be written as sigma C divided by EC. It means compressive stress divided by compressive strain. Okay, so this is the Young's modulus of elasticity, which is the ratio between tensile stress to tensile strain or compressive stress to compressive strain. Okay, next. And the next type is modulus of rigidity. So this modulus of rigidity is again called as shear modulus of elasticity. Why? Because this we are going to define based upon the shear stress that is going to take place over the body whenever we apply a shear force. Okay, remember another name is shear modulus of elasticity. So simple definition is again it is defined as the ratio of shear stress to shear strain. Okay, because of shear force we are considering, we have to consider shear stress and shear strain. So the symbol used for representing the modulus of rigidity is C or N or G. So these three letters are used to represent the modulus of rigidity or shear modulus of elasticity. Okay. So what is the formula we can write? The simple formula same in the form of the ratio C is equal to tau by ES. Tau is the shear stress and ES is the shear strain. Okay. In this form we can write the equation for the modulus of rigidity. Next, we go for third type. Third type is bulk modulus of elasticity. This bulk modulus of elasticity is also called as volume modulus of elasticity. Why? Because this elastic modulus is related to normal stress and volumetric strain. Okay, so related to volumetric strain, we are defining another modulus of elasticity that is only called as bulk modulus of elasticity or volume modulus of elasticity. So remember the another name for bulk modulus of elasticity is volume modulus of elasticity. Now, so what is the definition we can give? It can be defined as the ratio of normal stress to volumetric strain. Okay, so whatever the stress acts normal to the face of the body, so that stress to volumetric strain, okay, that ratio can be called as a bulk modulus of elasticity. And what is the symbol used? Symbol is the K used to represent the bulk modulus of elasticity. So K is equal to what we can write from the definition we can write sigma n divided by EV. Sigma n is the normal stress and EV is the volumetric strain. Okay, this is the formula we can write based upon the definition that is given to the bulk modulus of elasticity. Okay, so these are the three types of elastic modulus. Okay, the types are over. Next we are going to discuss about lateral strain. So we know longitudinal strain, linear strain, but what do you mean by here lateral strain? Okay, somewhat opposite to the linear or longitudinal strain here. So what do you mean by exactly lateral strain? So let us have a look first on the definition. So what is the definition? It is a strain that takes place perpendicular to the direction of the force applied. Okay, here the strain means is the deformation. So that deformation, how it is going to take place? Perpendicular to the direction of the force we are applying over the body. Okay, so the deformation related to the perpendicularly, that means here the strain taking place perpendicular to the direction of the force we are applying, that strain or deformation can be called as your lateral strain. So let us have one example diagram. Oh, sorry. Here, one more name we can give to the lateral strain is secondary or transverse strain. Okay. So secondary strain or transverse strain means similar to lateral strain only. Okay. Now we take one example to understand thoroughly about the lateral strain. So I have taken one body which is fixed at the top face, and now I am applying a load P. Okay. Due to this load, what happens here? It can be considered as a tensile load I am giving. Okay. So it will try to pull the body. Okay, so when we try to pull the body with the help of the force, any force P, there will be change in the dimension of the body. So how the change happens? There may be increase in length of the body. So whatever the length initially we are considering before applying the force, okay, that will be less than the length of the body after application of the force. Due to the deformation is taking place, there will be change in the length. So how the change has happened here in the length, that is increased, but at the same time what is happening to the side faces, the dimension is decreased perpendicular to the direction of the force. If you consider the direction of the force here, it is passing through the axis of the member only. Okay, so there is an increase in length along the direction of the force, and there is a decrease in diameter or size, whatever it may be, according to the cross section of the body we can consider. There is a decrease in dimension which is perpendicular to the direction of the force we are applying. Okay, the strain related to which is taking place perpendicular to the direction of the force we are applying, that strain is only called as your lateral strain. Okay, and we know already what is normal general strain and longitudinal strain, both are same, and it can be called as the linear strain also. So what is linear, longitudinal or primary strain means here? The strain which is taking place along the direction of the force, that is linear or longitudinal uh, or primary strain. Okay, but here lateral strain means which is taking place perpendicular to the direction of the force, so that strain or deformation is only called as here lateral strain. Okay, I hope you understood about lateral strain. Okay, which can be again called as secondary strain or transverse strain. Okay, that is about the lateral strain. Next we discuss about the Poisson's ratio. This Poisson's ratio is defined with the help of the linear and lateral strains only. Okay, so what is the definition means? This is the standard definition which is defined to give some standards to the different types of the materials. So later you can understand. So why all these terms are used? These terms are used to give some specifications to the different types of the materials. Okay, so for that purpose we have to know all these elements. So here we have to know what is Poisson's ratio. This is defined as a ratio of lateral strain to linear strain. Okay, just we have discussed about what is lateral, and linear strain already we know, that is the longitudinal strain. Okay, so the ratio between lateral and linear is called as your Poisson's ratio. Okay, so this Poisson's ratio is equal to, again, the formula we can write based upon the definition, lateral strain divided by linear strain. Okay, na? Next, the Poisson's ratio, the symbol used for representing the Poisson's ratio is mu. That mu is equal to, we can write it as 1 by m. Okay, here the Poisson's ratio specially represented as 1 by m. M is the symbol again here, that m can be represented in terms of the digits. That value will be varying for different types of the materials. So Poisson's ratio main symbol is used as mu. That mu is equal to, can be written as 1 by m. For the ease of representing the value of Poisson's ratio, This reciprocal of m, that is 1 by m representation, is used here for Poisson's ratio. So remember, the symbol is mu and it can be represented as 1 by m, which is equal to the ratio between lateral strain to linear strain. That is about Poisson's ratio. Next we go for relation between elastic modulus, relation between three types of the elastic modulus here. So first we try to derive an equation for the relation between E and C. What is E here? E is Young's modulus of elasticity and C is modulus of rigidity or shear modulus of elasticity. So what is the relation? Relation means the formula which will be representing the relation, representing in terms of two, that is E and C. Okay, so for that, first we try to consider one cube. Okay, for the ease of deriving the equation, we can consider the cube which is fixed at one end, and I am assuming the corner points as A, B, C, D. Okay, and here I am applying a shear force at one corner, that is B, at a point of B. I am applying tangentially to the surface here. This force has to be applied tangentially to the surface. So this force is shear force I am applying. Why? Because here the relation we are going to produce uh, between tensile or compressive stress and shear stress. So that is why initially I am taking help of shear stress. Automatically internally the body can develop compressive and tensile stresses. Okay, so for that sake I am applying the shear force, and due to the application of shear force, this top surface can face a shear stress tau. At the same time, this bottom surface can face shear stress which is in opposite direction, because it will be resisting the shear force which is taking place over the face, that is BC here. Okay na? So because of shear stress taking place over the surface, the body, that is ABCD cube, tries to deform in its in shape. Okay, that means it can change its shape. So it can, how it can change? In the form of angle. Okay, so this body has deformed to this dashed line shape. That means here the B point has moved to B dash and C point has moved to C dash. Okay, so this deformation, sorry, before that I would like to represent the diagonal. So this diagonal, if you consider the deformation of the diagonal also, that is AC, the diagonal will move to AC dash due to the deformation has been taking place due to the shear force we have applied. Okay, so now try to represent the phi. What is the phi here? That is the shear strain happened due to the shear stress is taking place over the surface due to the shear force here. So phi I am representing as the shear strain. Okay, so now we try to write what is shear strain formula. Already we know shear strain can be measured through an angle through which the body has distorted. So for giving the quantity, we can use the equation of tan 5 from the right angle triangle of any one of these two, either left hand side or right hand side, and the tan phi would be becoming equal to phi because phi is very small. So directly we write the formula, that is shear strain phi is equal to what we can write, opponent by adjacent. What is the opponent here? CC dash. So that is equal to CC dash divided by adjacent. Adjacent is CD. So shear strain can be written as CC dash by CD from this right angle triangle, which is obtained due to the deformation of the body. Okay, but there is another formula that is related to modulus of rigidity formula. We know the modulus of rigidity, just we have defined now. So from that modulus of rigidity also we can write the equation for shear strain. So what is the formula for modulus of rigidity? It is the ratio between shear stress to shear strain, that C is equal to tau by ES. So ES is the shear strain here. So this shear strain ES is equal to what we can write again, that is tau divided by C. Okay, this tau by C is also shear strain formula, and this CC dash by CD also shear strain formula. So we can make these two equations equal now. So now try to write the equation by making these two equations equal, that is CC dash by CD is equal to tau by C here. So assume this equation as 1. Now keep aside all these steps by highlighting the first equation. Next we go for the analysis of the deformation of the diagonal. So why you are going to consider the analysis of deformation of the diagonal means, here we need to form a relation between modulus of rigidity and elastic sorry, Young's modulus. So we need to consider the Young's modulus. That means tensile stress or compressive stress also. So for that sake, we are going to consider the analysis of the diagonal here. Okay, here what I would like to write, what is diagonal strain. Diagonal strain means what is the deformation has taken place to the diagonal AC. Any one of the two diagonals we can consider. Here I am considering AC diagonal. This has AC has moved to AC dash by having increase in length. Okay, this diagonal strain can be written with the help of the increase in length to the original length. So how can we represent the increase in length? The length has been moved to C to C dash. So to know the increase in length, we have to draw a perpendicular line from C. So draw a perpendicular line from C on the line of AC dash, okay, and represent the intersecting point as N. Now this NC dash becomes increase in length, and this AN can become that is original length, okay, because this CC dash is very small. Actually AC is the original length. This AN can also become original length because this CC dash is very small. So initially we try to write the ratio of increase in length to original length, which will be the diagonal strain, that is change in dimension to original dimension. So it can be written as NC dash divided by AN. Okay, this A in place of AN, what we can write? AC, because this CC dash is very small. This AN can become equal to AC approximately. So that is equal to, again, can be written as NC dash by AC. Okay, so this is the diagonal strain. Again, what is NC dash and what is AC in terms of known terms? That means known values, otherwise assume. In terms of known quantities, we have to get the equation. So that means here what is NC dash, what is AC, we have to derive. So keep aside this form. So now we try to write what is NC dash, what is AC. Okay, for finding the NC dash, let us consider the right angle triangle C and C dash, or C dash and C. This is the right angle triangle. Observe the cursor. This C dash and C is the right angle triangle. So now consider the right angle triangle C dash and C. In this equation, cos 45 is equal to, so what is cos 45 means here the angle between this CC dash and C dash n. Why it is 45 means because of the diagonal making an angle of 45 degrees with the side, the same angle can be made by the CC dash with respect to C dash n, because we are assuming this CC dash is very small. So the same angle can be transferred to the angle of CC dash uh, and n. CC dash n angle also can become 45 degrees. So this cos of 45 degrees from this right angle triangle, what we can write, this Cn is the opponent and this C dash n is the adjacent, and CC dash can become hypotenuse here. What is the cos theta formula? Cos theta formula is equal to adjacent side divided by hypotenuse. So cos 45 is equal to adjacent side means here C dash n, that is NC dash divided by CC dash we can write. Okay, so now we have to know what is NC dash. So try to write the equation in the form of NC dash is equal to. So before that, cos 45 I have mentioned. The cos 45 is equal to, all we know, 1 by root 2, that is equal to NC dash divided by CC dash. So now try to write NC dash is equal to, NC dash can become equal to CC dash moves to the numerator. So CC dash divided by root 2. This is the NC dash value we got. Okay, for writing in this diagonal equation. So keep aside this one. Next, we go for finding the AC. So what is AC? So for finding AC, we need to consider the right angle triangle ACD here, or ADC here we can consider. Okay, from the right angle triangle ACD or ADC here, actually we can write it as ADC because the right angle is taking place at D. Okay, so in this equation, cos 45 is equal to, what we can write, this cos 45. So this cos 45 is equal to, again we have to write adjacent side divided by hypotenuse. So adjacent side is CD and divided by hypotenuse is AC. So here we have to know what is AC. So for writing AC, first try to write AC is equal to CD divided by cos 45. Cos 45 means all we know 1 by root 2. So now this root 2 can go to the numerator. So this AC is equal to, we can write it as CD root 2. Okay, this is the AC we got. Okay, we have to know what is NC dash, what is AC. We got NC dash here, we got AC here. Now keep aside this one. Now try to substitute this NC dash and AC in diagonal strain equation. So diagonal strain is equal to, okay, by substituting NC dash and AC in diagonal strain, what we get, try to observe. So diagonal strain is equal to, in place of NC dash, what we have to write, this CC dash by root 2. So CC dash by root 2 divided by, in place of AC, we have to write CD root 2. So that CD root 2. Okay, so root 2 comes to the denominator again. So root 2 into root 2 will be getting, that is CC dash by root 2 into CD into root 2. Okay, keep aside and modify this equation, that is CC dash divided by 2 into CD. So diagonal strain we got as CC dash by 2 into CD. Now go to the equation 1. So how the equation 1, CC dash by CD is equal to what we got, tau by C. So here CC dash by CD is there. So in place of this CC dash by CD, we can write tau by C. So now from the equation 1, we can write diagonal strain is equal to tau by 2C. So in place of CC by CD, we are writing tau by C. So which will become tau by 2C. And it can be again written as here sigma n by 2C. So why are considering the sigma n means, due to the shear stress is taking place over the face of the body, internally it can form normal stress also. This normal stress is the combination of a tensile and compressive stress is going to take place inside the body. When you consider diagonals, you can understand where the tensile and compressive takes place. So here when you consider this AC, there is a, sorry, before that assume this equation as 2, and when you consider diagonal, this diagonal is undergoing the elongation means the tensile stress takes place to the diagonal. When you consider this BD diagonal, what happens here, there is a compression takes place, that means it undergoes compressive strain. Okay, so here normal stress is combination of these two. Okay, so by the combination of these two effects, we can consider in place of shear stress as a normal stress here. Okay, so now assume this equation as 2, that is sigma n by 2c as second equation. Now next go for another form of writing the net diagonal strain. Okay, another form of writing the diagonal strain by considering tensile strain, sorry, linear strain and lateral strain. Okay, so linear strain, from the equation of Young's modulus of elasticity, we can write sigma n by E, and plus by considering the lateral strain, we can write it as sigma n by me. So these two terms are can be written by considering the linear strain and longitudinal strain. This is obtained from the normal formula of Young's modulus of elasticity, and this equation is obtained from the formula of Poisson's ratio. Okay, by considering the Poisson's ratio, that lateral strain whatever it is there in the numerator, we can write this form, because the Poisson's ratio is equal to 1 by m, that 1 by m is equal to lateral strain by linear strain. Again, the linear strain can be written as normal stress divided by uh, Young's modulus. So from that we can get this sigma n by me. Okay, in these two terms sigma n by e is common, so take the sigma n by e as common, then write it as 1 plus 1 by m. Okay, again assume this equation as 3. So when you consider this 2 and 3, both are related to diagonal strain only, so we can make these two equations equal. Okay, so by making these two equations equal, we can write sigma n by 2c is equal to sigma n by e into 1 plus 1 by m. So sigma n common, they can be cancelled, then e goes to the left side and 2c comes to the right side. So e is equal to 2c into 1 plus 1 by m we can write. Okay, this is the equation which will be giving the relation between, sorry, giving the relation between this Young's modulus of elasticity and the shear modulus of elasticity or modulus of rigidity. Okay, this is the final equation that is very very important. You have to remember the formula that is stating the relation between E and C. Okay, so I hope you understood this derivation part. Next we go for derivation for the relation between E and K, Young's modulus and modulus of, sorry, bulk modulus, that is volume modulus of elasticity. So for this we try to assume the same cube is subjected to compressive stress on the top face. So why are considering compressive stress, which can cause the change in volume with considered levels. Okay, so because of the relation we need to consider that is Young's modulus and bulk modulus. Bulk modulus is related to volumetric strain, and the Young's modulus is related to tensile or compressive strain. So wherever the large amount of the volumetric strain happens, that case we need to consider. So for that we are considering the compressive stress. So by the application of the compressive load, we can observe the compressive stress. So here the cube is taken. That cube is applied with compressive stress. By applying the load in this direction, it can cause the compressive stress. So along the direction of this load, the compression takes place, but perpendicular to the direction of load, the two directional tensile stresses takes place. Okay, one single direction of compressive stress is causing two directional, that is if you assume x direction and y direction. Okay, two directional tensile stresses are taking place. So here total strain is equal to what we can write, total strain in terms of stress and Young's modulus. This can be written as sigma n by E is 1 related to linear, that is the required linear strain, plus minus 2 times of sigma n by me. Okay, this is term related to linear strain, and this is term related to by considering the lateral strain. Why? Because these two stresses are in lateral direction. Okay, these two stresses are causing the lateral strain in the body. So two are acting in opposite direction. Okay, opposite to the initial stress that we are creating over the top face of the body. So that is one negative sign we need to consider, and the two types of the stresses are, two times the stress is taking place. That is why we are considering two times of strain. Okay, so total strain in the body can be written as sigma n by E minus 2 into sigma n by me. So once again I am telling you, this formula is obtained by considering the normal Young's modulus equation, and this relation is obtained by considering the Poisson's ratio equation. So this is related to linear strain, and this is related to lateral strain. Okay, that is subtracted from the linear strain for getting the total deformation in the body. So in this term again, sigma n by E is common. So sigma n by E into 1 minus 2 by m. So assume this equation as 1, or otherwise keep aside. Now try to write volumetric strain. So volumetric strain in this case can be written as 3 times of total strain is happening for the body. Okay, why? Because in three directions the deformation is happening. So the volumetric strain can be written as 3 times of total strain is taking place inside the body. So this EV is equal to, we can write 3 into sigma n by E into 1 minus 2 by m. Okay, again keep aside this equation, these two equations, and try to write the volumetric strain equation by considering the bulk modulus of elasticity formula. So what is the bulk modulus of elasticity formula? K is equal to, we know that, normal stress by volumetric strain. This is the standard formula that we have already discussed while defining this bulk modulus of elasticity. So from this equation, EV is equal to what we can write? EV is equal to sigma n by K. So this is volumetric strain, and this above equation is also volumetric strain. So we can make these two equations equal. So now try to make the two volumetric strain equations equal. So it can be written as sigma n by K is equal to 3 into sigma n by E into 1 minus 2 by m. Again on both sides sigma n is common, then they can be cancelled. Now take A to the left side, K to the right side. So it becomes E is equal to 3k into 1 minus 2 by m. So this is the relation, this is the formula which is giving the relation in between E and K, Young's modulus of elasticity and bulk modulus of elasticity. So remember this relation also, very important relation. Okay, that is E is equal to 3k into 1 minus 2 by m. E is the Young's modulus, K is the bulk modulus, and m is related to Poisson's ratio. 1 by m is the Poisson's ratio here. Okay, now, so finally we try to write the two relations we got. That is first relation in between E and C, E is equal to 2c into 1 plus 1 by m, and next we try to write E is equal to 3k into 1 minus 2 by m, and the third relation also we get, which will be giving the relation between these three, E, C and K. So that relation is obtained as E is equal to 9kc by 3k plus C. So how this relation is obtained means here by combining these two. So how can you combine these two means here, from this first relation try to write the equation what is m is equal to, modify this one and take the m as common, and write the equation in the form of m is equal to. So whatever the relation you are going to get, m is equal to, substitute that m in this equation and again modify this entire equation, then you will be getting this relation, that is 9kc by 3k plus c. So try to solve these steps. Okay, so if you are having any doubts in deriving this relation, that is 9kc by 3k plus c, please feel free to give a comment to my video so that I'll try to clarify. Okay, so I hope you understood the basic terms and the relation between elastic moduli, that means different types of elastic modulus. Okay, if you still have any doubts, please feel free to give a comment to my video so that I'll try to clarify your doubts, and don't forget to subscribe to my channel. Once again, thanks for watching. Thank you all.